All right, so last time we talked about transient conduction problems, and we specifically spent kind of a lot of time talking about this idea of a thermal wave and time constants. And basically, the whole idea is just that it takes time for energy to move inside of an object. It takes time for energy to move by conduction, which we sometimes call diffusion. And that time is is approximately related to how far it has to move. And we had this equation, which I will try to write. Delta sub t is approximately equal to 2 times the square root of the thermal diffusivity times time. So that's an equation that I think we ought to sort of just keep in mind as we move forward, right? We'll put it right up there with our resistance equations, which were pretty important, and the lumped capacitance time constant, which was pretty important. All right, and that was basically what we got out of last time, was this sort of conceptual idea of how conduction works, transient conduction works. So the other thing we did last time was an example, and it was actually this example here where we had a current lead, and it had been running for a long time with some energy generation, and it was being cooled, and then at some time we shut the current lead off, and what that did then is turn the generation off. So now there's no generation after what we're going to call time equals 0, and it also deactivated the cooling, which caused this heat transfer coefficient to go down. And we used this equation here to try to understand what that equilibration process looked like conceptually. And what we're going to do today is look at the equilibration process exactly using an analytical solution to this problem. So this is a bounded problem, which means that our tool for analytical solutions is going to be separation of variables. So we already talked kind of a lot about separation of variables for steady state problems. The exact same technique can be used for transient problems. So here's our transient problem. We're going to look at the equilibration process. So we're looking for time, looking at the temperature distribution at times greater than 0, right? And our initial temperature distribution then is the steady state temperature distribution that you get in the current lead. So we had some kind of steady state temperature distribution that was related to the thing operating for a very long time, right? So this is our initial condition. We want to derive the rest of the mathematical problem, so that includes the differential equation we have to solve, and this is going to be a partial differential equation because it's going to involve both time and position. And then we need boundary conditions, so a boundary condition here at x equals 0, and a boundary condition here at x equal L. So let's start by deriving the differential equation. We've done this several times at this point, so shouldn't be too hard. We define a differential control volume. So this is differentially small in the x direction, since temperature is varying in the x direction. We do an energy balance on that. So in equals out plus stored. In is conduction in the x direction at location x. Out is conduction in the x direction at location x plus dx. So this is coming in, this is coming out, and then stored is whatever energy is being stored inside of that control volume. So in equals out plus stored. Then we have the next step, which is expand the x plus dx term and take the limit as dx goes to 0. So that gives us this right here, and of course this cancels, and so we end up with this differential equation right here, right? And as always, we end up with a differential equation that is written in terms of energy, because that's always what we're trying to do, is balance energy. You don't balance temperature, you balance energy. This basically says that the rate of conduction heat transfer in the x direction isn't constant, and the reason it's not constant is because energy is going to be stored, right? Which makes sense. That should sort of be how it works. So this is a differential equation that's useful, but isn't the one we want to solve. We want to turn it into one that's related to temperature. So we have to substitute in rate equations. So this is a conduction heat transfer So we use Fourier's law here, right? It's in the positive x direction, so minus k AC dt dx. And then this is just the heat capacity inside of our control volume. So the heat capacity inside of this little differential slice, which has volume of AC times dx, and then rho times c times the rate at which its temperature is changing. So if I make these two substitutions, I get this differential equation here. We'll divide through by the everything that's constant in the highest order derivative, so minus k times AC. And what that gives us then is this differential equation here, right? This is thermal diffusivity again. Thermal diffusivity shows up over and over again in transient conduction problems, and we'll see it shows up a lot in convection problems as well. All right, so there's our differential equation. We have our initial condition. We need two boundary conditions. So one boundary condition is right here at this line of symmetry. Lines of symmetry are adiabatic. There's no reason that energy would ever want to come from over here and go over here, since exactly the same things are happening on both sides. So that says the rate of conduction has to be 0 at x equals 0. And according to Fourier's law, that says that the TDX at x equals 0 has to be 0. And then over here, we have convection, right? And so we have conduction going into that boundary equals convection from the boundary. So here's our math problem. It's a partial differential equation. We can solve it using separation of variables, and we'll use exactly the same steps that we used when we were doing steady state problems, right? So step one is just look at our problem and see if it meets all the requirements that you have to meet in order to apply separation of variables. So those requirements are listed here again. The partial differential equation and the boundary conditions should be linear. They all are linear. We are dealing with a very simple computational domain. The partial differential equation should be homogeneous, and it is. And then both boundary conditions in one direction must be homogeneous. So I only have one direction here, and that's the x direction. So both of those two boundary conditions have to be homogeneous, or I can't use separation of variables. And they aren't, right? One of them is, this guy here, though, is not, right? That's not a homogeneous boundary condition. So I have to do something to get rid of the non-homogeneity in this boundary condition before I can apply separation of variables. And in this problem, it's very easy, right? I know that I can always get one more homogeneous boundary condition just by solving for temperature relative to some reference temperature, in this case T theta, and that would make this boundary condition homogeneous. In some cases, it's not that simple, and the homework, depending, I guess, on when you're listening to this, in the homework, you'll find that that's not going to work, and you have to do something a little bit more complicated to get the problem broken into a problem I can solve using separation of variables, and then a problem that I can solve in other ways. All right. So in this case, though, I see the path forward. The path forward is, let's just solve for theta instead of t. If I make this substitution into my original problem, this is what I get. So here's the partial differential equation. Here, the initial condition changes just a little bit, right? If I'm solving for theta, this t infinity goes away. This boundary condition doesn't change, and then the payoff is right here. This boundary condition went from being non-homogeneous due to that term to being completely homogeneous. So now I can solve this using separation of variables because both of my boundary conditions in x are homogeneous. And x then is a homogeneous direction. X, just looking ahead, x has to be my eigenproblem, right? It's my only direction. It has to be my eigenproblem. I know exactly what ODE has to be related to the x direction, right? I know that I'm going to get eigenfunctions. I'm going to have an eigencondition that gives me eigenvalues, and those eigenfunctions are going to be orthogonal. All that stuff we learned before, we'll use here again, right? Okay, step 2 is separate the variables, right? So same idea, right? My theta here is a function of both x and time. And what I'm going to do is assume that it can be written as a function of x multiplied by a function of time. And I just take that idea and plop it into my governing differential equation. And what should happen is I should turn that problem into two ordinary differential equations, right? So that's what I did here. I put theta x times theta time in every place that I had a theta. And then I recognize that any place I'm taking a derivative of x, a derivative with respect to x, theta time can just pop out. And any place I'm taking a derivative with respect to time, theta x can just pop out. And that gives me this here. And then if I want to get all of the x stuff together in one group and all of the time stuff together in another group, I'm just going to divide by theta x times theta time. And that gives me this equation here, which is exactly what I was looking for, right? This is only a function of x. This is only a function of time. The only way this can be true everywhere is if these two functions, if these two groups are equal to each other, obviously, and equal to a constant, right? So then the only thing that's left is just, is it going to be a positive constant or a negative constant? So that's what I did here. I said these two groups have to be equal to each other and either a positive or a negative constant. How do I decide whether it's a positive or a negative constant? Well, I do that the same way I did before, and that's by knowing what it is that I have to get for an ODE in my homogeneous direction, right? That's not an arbitrary thing. It's important that I get a certain ODE, and that certain ODE is the one that gives me sines and cosines. So if I solve this equation here, I get this, right? If I solve this equation here, I get this. And I know that I have to get this ODE right here, right? So that means I got to choose the positive constant. If I choose the positive constant, that means that I got to get this ODE for time, right? I don't actually care what I get for time. I have no requirements there. I care a lot what I get here, right? I know I have to get this ODE. So that's separating the variables. The next thing to do is solve the eigenproblem, right? So here's my eigenproblem. I went to a little bit of work to make sure this is the problem I have in x. It's solved by sine and cosine, right? If I want to figure out C1 and C2, I need boundary conditions, right? So one boundary condition, they're both homogeneous. One is at x equals 0. So if I take the derivative of this and evaluate it at x equals 0, I get c1 times lambda times the cosine of 0 minus c2 times lambda times the sine of 0. And cosine of 0 is 1, and sine of 0 is 0. So this equation tells me that c1 has to be equal to 0, right? So if I plug that back up into here, it gets rid of my sine terms, and I'm left with only cosine. So my eigenfunctions for this problem are going to be cosines, right? That's always what I get from the first boundary condition, is just what is the form of my eigenfunctions. And sometimes they're sines and cosines. Sometimes they can actually be combinations of the two. But that's what I should get by enforcing my first boundary condition. My second boundary condition better give me my eigenvalues, right? That's what's happened in every problem we've done so far. That's what should happen here. So here's my eigenfunctions. I'm going to plug it into that second boundary condition. So let's see, I got to take the derivative of this, which is c2 times lambda times sine lambda L. And then, I'm sorry, minus, the minus cancels this minus. And then this is h bar times c2 times the cosine of lambda L. So this, if I rearrange it, I have sine over cosine on this side, and over here I have h bar and then a k and a lambda, and the c2's cancel from both sides. Sine over cosine is tangent, so I have tangent of lambda L is h bar times L over k times lambda L. So this is my eigencondition, right? Again, whenever I have a convective boundary condition, I'm going to get an eigencondition that is not super easy to find the roots of, but definitely there are as many roots of this eigencondition as I want to look for, right? This can go on forever. This isn't very different than what we had before. If I plot the left side of this eigencondition tangent, you can see it sort of repeats this pattern of going from negative infinity to positive infinity every pi, right? And if I plot the right side of this eigencondition, it's some constant. That constant's actually the BO number, divided by a lambda L. So it's a parabola, right? It goes like this. So every time this parabola intersects tangent, I'm going to get an eigenfunction, right? So here's my first eigenvalue, there's my second eigenvalue, my third eigenvalue, and so on and so forth. And the really important thing about a graph like this is just figuring out where the different regions are where I should search for these eigenvalues. So I should search my first eigenvalue between 0 and pi over 2. I know I'm going to find my second one between pi and 3 pi over 2, 2 pi and 5 pi over 2, 2 pi and 5 pi, this should be 3 and this should be 4, sorry. So 3 pi and 5 pi over 2 and so on and so forth. So in general, this is my equation that gives me all of my lower bounds on these regions and all of my upper bounds on these regions, right? So now it's just a matter of going to whatever software you're going to use and doing a search in each of these regions to find as many of these eigenvalues as you're interested in finding. So we're going to use ease to do that.